party got finished this morning on my side. But anyways, so we're still on this track that we want to kind of transfer our knowledge about excitons from condensed matter, but they have been known for a very long time, since the 1930s actually, to our new toy systems, these Rydberg systems, Rydberg aggregates. And I told you yesterday what the motivation was, and that's of course still the same. And it's like always the scheme that with these ultra-cold Rydberg systems, you have much better access to the processes and the dynamics. You can manipulate them much better, can look at them much better, and can basically gain understanding in an easier way as compared to the systems where the similar processes happen like condensed matter systems or in these two biological relevant light harvesting complexes, for instance. So what we had yesterday, we said if we want to transport really electronic excitation across many sites, then we want to do that, of course, coherently. And what limits us are decoherence processes. And the most important source, of course, is atomic motion itself. I mean, the electrons find the atoms always somewhere else, and that is a source of decoherence. In condensed matter, that's phonons, just lattice vibrations and so on. And we said that in essentially a bound molecule, this is like coherent forever, because there the nuclear motion and the electronic motion is so well intertwined that they don't decohere each other. This is just staying there forever. I would like to use something like that for transport in the continuum. That's of course different boundary conditions. If you set a wave packet, it's per definition not possible. The wave packet itself disperses already. But still, one would like to also intertwine the atomic motion and the electronic excitation in a similar way as is the case for bound states. And that's the idea of these excitons I will come to. We want to use the force our dipole-dipole interaction exerts onto the atoms. We want to use this force naturally to transport electronic excitation across many sites. And today we will have basically, we said we need two ingredients. Yesterday I spoke basically about the part which is kind of relevant for the atomic motion, the slow part, which also tells you, since this is so much slower than the electrons, that you can make an adiabatic separation. And that's of course very important. That's one of the key concepts in physics at all. And I think this is basically the reason why you live in the world you live and why you have differentiation of many things. This adiabaticity, separation of time scales and so on. And today I will talk about the other part, the electronic part, really what are the concepts for an exciton, traditional concepts of an exciton in condensed matter. But I promised you yesterday, the last bit here, time from space, in terms of crazy ideas about adiabaticity. So this is what we want to start with this morning. And like always, things like this get started in a coffee conversation, in a morning break somewhere with your group. I think it got started when I was still, not a student, but a postdoc. And we kind of started to debate about the uncertainty relation. And we all know the uncertainty relation. Delta P times delta X is derived from the commutator of momentum and position. And of course, this is at the heart of quantum mechanics. It's a true operator-based relation, the uncertainty relation. And you probably also know, as we all do, that there is this uncertainty relation delta E times delta T, energy and time. But this is of course not an operator-based uncertainty relation, because time is not an operator. Time is just a classical variable. So essentially this is just a Fourier relation going from one space to the other. And the question is, of course, why is that the case? I mean, it's very strange, right? And once we discussed that heatedly in our coffee round, we realized, okay, we're not the first ones who discovered that. I mean, there are really famous people thought about that and banged their head against the wall. I mean, all the famous people you know, Wigner, God knows what. And so there are essentially two routes researchers have followed to solve this problem. One route is, of course, try to find a time operator. If you find a time operator, then you're done, because the Hamiltonian certainly is an operator, yeah? And then you could construct a true uncertainty relation. And the other route is, of course, try to argue that time is a derived quantity and that the asymmetry between these two uncertainty relations is just a consequence of the fact that time is not an original or deeply rooted quantity, but just basically a convention. And I had the luck to spend 1 year in an advanced study institute in Berlin, together with my former advisor, John Briggs. And we were a group of 4 people. So 2 tried to prove this one, and the other 2 tried to prove that time is a derived concept. And so the leading guy among them who wanted to construct a time operator was actually Martin Gutzwiller. But he gave up after 3 months when he realized that essentially there's really very big obstacles to do that. You have principal reasons why you cannot find a time operator. One has to do with causality and so on. And so we were happily carrying on, and the result of this carrying on, why time doesn't exist, I will present to you now in a nutshell. All right, so I mean, in this advanced study institute, we were the only 4 physicists, so we had to justify our existence every day towards historians and, poet in residence with the name Adonis, by the way. And he won the Nobel Prize 2 years later for literature. That's not so bad. And composers in residence and all kind of interesting but crazy people. And so we need to find arguments about what we're doing formally, which are not formal, right? Because they don't understand math and they wouldn't take it for granted anyways. And this was actually very healthy. So, what about time, if you reflect on time? And first of all, you know conservative systems. You all know, right? Energy is conserved. Does one need time to describe a conservative system? No. Yeah, you can basically take any kind of path variable out of these coordinates of your system to make the system progressing as a function of this path variable. And that's of course possible because the energy is conserved. You can eliminate time from there. And one could also think if Poincaré would have, been born before Newton, we might have a very different understanding of nature and of physics, because Poincaré really had the phase-based approach. Momentum and position, time was, not so important. While Newton, of course, lived in the world, and you all know, developed Newton's equations, which are, of course, all functions of time. Yeah, and then you think about, how is it about time? Is it really so essential? And if you think about something essential, you always think about kids. When do they actually learn about time? Do they know about time from the beginning? And this is something very interesting. I stepped then across reading a little bit about the developmental psychology, I think that's called in English. And you realize that there are many experiments. Piaget was the forefront man of that in France, who discovered that kids actually do not have any sense about time in the beginning. Yeah? And they only get some idea about time when they kind of almost turn 3 years old but this is not so decisive. This can, vary quite a bit from one kid to another. What is actually linked to the phenomenon when they start to be more realistic about time is when they can say I. In the beginning, you probably also know every kid says his name. I don't know, Peter is doing that and that if they speak of themselves. They always speak of themselves in the third person. They don't say, this is me and this is the world. They're kind of part of the world, or they're distant themselves because they don't have this identity yet. But when they start to develop this identity, which is signified by being able to say I, as opposed to you and the rest of the world, then they start to get a reliable sense about time. Very interesting. That means time is somehow connected to your ability to distance yourself reliably from your environment. When you think about that, you can find many more actually phenomena where this is true. One very crazy one, and this was just to upset these guys and the colleague there, is of course that in dreams, time is not a concept, right? Time goes totally crazy in your dreams. You probably have had some dreams where this was really true. And you can find a justification for that by saying, well, yeah, I'm not distant to the environment, to what surrounds me in my dreams, because it's not there. I'm not conscious in that way. Hibernation is another interesting phenomenon. Also, time does not basically flow in that way when an animal is in hibernation. And the reason is simply that basically it decouples itself to a large extent from the environment. Yeah? The exchange of everything, oxygen, any kind of things, is just lowered. And time goes slower, quote unquote. Anyways, and you can also think why we actually really, in the end, as living beings, can have a concept about time and can have contact with the environment. And this is essentially because we are breathing. We are in constant exchange, even materially, with our environment. If we are not, we're dead. It's gone. Yeah. Anyway, so this is a bit philosophical, but it's important because it really gets you more and more the idea that time is somehow connected with the existence of separation. So if everything is one thing, there's no time needed, there's no reason for time, and time comes into play when things are separated. And there was one guy actually who was a professor for religion or something like that from the church. And of course I gave him the example of the paradise, right? Being expelled from the paradise. Because in the paradise, there's no time. And time starts when Adam and Eve got expelled to the earth. And you see that because there is done this generations of fathers described in the Bible. That's a clear sequence of time. Yeah? Before, there's nothing. So again, separation. Anyways. But he was very clever. He said, okay, now since you abandon time, should you not also abandon space? And that left me a little bit speechless. All right. Now, this doesn't work. Yeah. So let's try to formalize that. So we want to start from something definite, and this is we take everything we have, and if something is still changing, then we have not included everything yet. Yeah. So because if we have included everything formally in what we described, then nothing can change in this everything. Within it can, but the thing itself cannot change. So therefore we start in a way with a closed quantum system in an eigenstate which encompasses the entire universe, whatever you want, in an abstract way. And it has the fundamental equation you all know, h equals e psi, h psi equals e psi. But now nothing can change. It's quite boring, and this is not what our daily kind of experience is. So now comes the separation. We take out a little subsystem. This is you, me, whatever. Now, of course, we have this relation. This everything is now what's left after we have taken out this little subsystem. Then the interaction between the subsystem and what's left, and the subsystem HS itself. And now you can already smell where this goes to, right? This is a molecule. So this is essentially a big environment, all but little subsystem, and this all but a little subsystem is nothing but the nuclear degrees of freedom, which are very slow and inert, and they don't care about the subsystem. They are kind of the reference frame. And the subsystem is kind of the electronic degrees of freedom. It's fast, small, vulnerable to influences from your environment here. This is exactly what electronic degrees of freedom are. And this is exactly how we describe that now. We say our total wave function for the entire system is separated in degrees of freedom x, which belong to the subsystem we're interested in, and to the environment, described by coordinates r. So this can be many, can be a vector, yeah? And we take this as an adiabatic wave function, you all know, like for molecule. For the environment, this would be in the molecule the vibrational wave function times the wave function for our test system we're interested in, and for which we want to derive time, by the way. Yeah, that's the goal. We want, in the end, want to derive the time-dependent Schrödinger equation for this little subsystem x, which will be based on the reference to all the environment. And this is, of course, just an adiabatic molecular wave function. And I should mention maybe one more motivation, I forgot, with all this kind of psychological stuff, which is much more realistic, if you wish. And this is, how did people measure time until the 60s? They measured time basically by the planets. And the planets, do they move in time? Well, that's what you think. They move in space, right? They change their angle, they change basically their position. And what you really measure time, you measure time in terms of change of positions with respect to you as an observer. So there you measure, and have measured quite directly for centuries, time in terms of change of position. Anyways, and so we replace now abstractly, if you wish, your planets and so on with this big environment here. So now, what is really important is this asymmetry condition. Yeah? The system is much, much smaller than the rest, and therefore the system can be influenced by the rest, therefore it depends parametrically on capital R, while the rest does not care about the system and is not influenced. Again, like nuclei and electrons. And now comes another thing. So this is this asymmetry condition, also expressible in terms of energies. If we basically calculate the energy of our environment here, then this is much, much larger than the energy of the system. And because this is so large compared to that one, we can make, or we assume we can make, a semi-classical ansatz to describe the environment to start with. And this we do now. So we make the Born-Oppenheimer approximation as here. And in addition, and that's a little bit different as compared to, of course, nuclear vibrations, we describe right from the beginning our environment, what is the analog to the vibrational wave function, as essentially a semi-classical WKB type of solution. Do I have this somewhere here? Yeah, here it is. So just amplitude times e to the I action. And now we can insert this wave function here, yeah? This complete wave function here with the semi-classical approximation for the environment. We insert that into the full Schrödinger equation for H and see what happens. So this is done here. This is already separated because we know that the semi-classical wave function solves the Hamiltonian for the environment, and this is now left for our system. So it's a little bit upside down for Oppenheimer if you wish. That's all fine. This is kind of, yeah, the system energy as a function of the external parameters and so on, like one Oppenheimer potential curves, system Hamiltonian, the coupling, and here is the coupling, of course, of our wave function of the system, which depends somehow on the coordinates of the environment. And this will be the time derivative in the end. This will give us the time-dependent Schrödinger equation, the reference to where the environment is with respect to the system. How does this work? Well, if you use this WKB wave function, you can simply see what the CI is. This is just only inserted, so there's nothing magic here. And now we, of course, take in, to be consistent with the WKB ansatz for the environment, only the lowest order in H bar. And that means the CI reduces essentially to this term. This is already higher order in H bar. This is lowest order. And this lowest order in H bar is just, as you see here, 1 over mass, action differentiated with respect to position. You know classical mechanics, what is that? That's momentum. Yeah? So we get basically here momentum, and therefore this is then in total basically this derivative. If you put this together here, CI is now a directional derivative in all the coordinates of the momentum. You can write that as velocity in the end with this m, dr by dt. And of course, the rest is left, like always in Born-Oppenheimer, is the gradient on the other wave function, the psi, and this gives you then this directional derivative, and if you just add that together, this is a simple scalar derivative, which you might call d by dt time, and it is actually even unit-wise time, yeah? Because you see that quite clearly here. That means we finally get from the coupling to the environment, these are the non-adiabatic couplings in molecules, we get a time-dependent Schrödinger equation for the system. There you go. So we started out with the time-independent Schrödinger equation for everything, took out the little system, and the relation to what's left of the big whole entire universe, this relation gives us the time derivative here, and gives us the time-dependent Schrödinger equation. Yeah, that's about it. And now you can see how energy time uncertainty works. So in general, we have this relation for two observables connected with their uncertainties based on the operators. Now we take, let's say, A as the energy of the environment and B the coordinate of the environment. Then, of course, this kind of uncertainty gives right away expectation value of momentum over mass. Now, since the environment is really semi-classic because it's so big, we can write that as delta R equals velocity times delta T. So that this translates now in the end to delta E environment times delta T much larger than h bar over 2. And this is clearly a parameter relation, which is okay, yeah, because the environment is semi-classically large. And now, since essentially we know that the total energy is conserved, we can directly, we know that delta total E is 0, therefore delta fluctuations in the energy of the environment must be reflected in fluctuations of the energy of the system. It's not possible in a different way, and therefore this implies really then the energy time uncertainty for the system. But we started out with a true operator-based uncertainty in position actually for the environment. No, this was our explanation how that works. Anyways, so this is the idea why time does not exist or why time is just an illusion. And you can think of many, many examples. You will see that at least this idea that time comes into existence by separating objects in space makes a lot of sense. Okay, now this is maybe even more provocative or even really wrong, I don't know. But so we have kind of tried for quite a while. I guess right now we have given up because at some time you'd be bored. To find a proof for that. I mean, in physics, right, you can claim anything, but the good thing is, that's why you're doing physics, essentially you should prove that experimentally, otherwise it's pointless. And the problem is, of course, that, and I didn't say that, it's the asymmetry condition. I mean, we all have the feeling or know that time is absolute. Yeah? The way I construct time is certainly not absolute because it's coupling to the environment, and it depends on this coupling. And only if this environment is so big that any back reaction does not play any role, the time is absolute. So it's absolute only to the extent that the back reaction from the environment on the system is negligible. And that's the point where one should find a system where this back reaction is not negligible. And unfortunately, we were not able to find such a system because whenever you measure something, you're automatically macroscopic. And you kind of quench this back reaction. At least this is our present working conclusion. Which also makes, in a way, a lot of sense. Yeah? But this might be an example where actually really time simply does not make sense. It's an odd example. And this, I don't know, this put me in a lot of excitement when I learned about it in grad school, because this is an experiment, a deterministic experiment. You know exactly what you're doing, and you never can reproduce it. And I thought, this is outrageous. I mean, how can that be? This is physics. I mean, this is reliable, and it's, So what this is essentially, you have basically, where do I have this? Yeah, you put basically, you excite an atom in a trap, power trap or something like that, and then you observe, drive a transition, 0-1, optically with a laser, and the point is, I should point it here. So you drive this transition, and there's a third state, which is weakly coupled. It's kind of parity forbidden or whatever. So off and on, the electron gets kind of parked there, but then there's no electron to drive, and no electron to come down again to get fluorescence light, so it's dark. And essentially, this is what has been observed then. Basically, the fluorescence of this transition from level 2 down to level 1 as a function of time. When you see light, and then you get dark intervals. You see light again, you get dark intervals. Whenever this electron gets shelved, as it's called, in the third level, which is weakly coupled, there is a break, and only when it decays again to the ground state much later, it can be driven again, and you see the fluorescence. Now, this sequence is not predictable, and it's not reproducible. The only thing which is reproducible, of course, is on average, or the sum of all the lengths of the dark intervals and the sum of all the lengths of the bright intervals, because that's kind of the lifetime of this level. But this is a realistic experiment. It's deterministic, and it still doesn't. So, my interpretation would be now, that's all fine, but essentially time does not make sense. You should not plot basically your bright light and your breaks against time. And why is that? Let me try to explain that to you. What we do here is we couple two small systems together. Yeah? And if you couple two small systems together, according to my ideas about time, time doesn't make sense because you need this asymmetry condition. You need a big system which does not permit any back coupling. If two small systems are coupled together, they will influence each other, and time simply doesn't make sense. So, what are the two small systems? Well, one is clear. It's basically the electron to the three levels here, and here in the system 1, 2, the electron is coupled to an environment which contains many photons. This is where you drive the optical transition. Yeah? That's a strong laser. So that's no problem. If you drive it and you have kind of this environment of photons which is large, that's okay. But the system 1, 3 plus light is actually really small, because here you have no photons. You have spontaneous emission, right, of this weakly coupled level down to the ground state. So essentially, there's no number density in the photons here, and also only 3 states in the electron. So here you couple the small massive system with the 3 states for the electron to a very small optical system, which is essentially vacuum. And this does not permit time in a way. That's my interpretation. Now, what do you do when you actually kind of sample or average over many of these intervals? You actually make many identical copies of these small systems 1, 3 and add them together. And this effectively gives you a big system again. And then it works out. That's kind of the idea. Okay, you can kill me for that later on. You have now 20 more boring minutes about excitons to think about that, and then we can talk about it. But that's my duty, so I should tell you about excitons. So we're done now with the adiabatic stuff, and come now really to the question about electronic transport for fixed nuclei, and this is excitons. So I'll first tell you a little bit about the general concept, and these two different approaches by Frankel and Vanier, and also Mott, that's kind of the same thing. And then we'll specialize that to molecular aggregates, and we'll discuss in some detail the minimal unit of an aggregate. That's 2 molecules, a dimer, right? How they exchange things and how energies get basically changed there. Then excitons and largest, and I will discuss transition moments. That's a bit what we did yesterday, but here now specialized to the excitons again. Dipole-dipole coupling and absorption. And come then to excitons and larger systems, and I will probably skip the general part for your mental health because it's a lot of indices. And we'll right away come to linear J aggregates, which is still bad enough. But this is then a linear chain of these molecules, of identical basically units. And this is what we want and what we need, because still keep in mind what I want to do, and I will do that finally of course in the last lecture. I will take basically a chain of Rydberg atoms, yeah, and we'll have excitonic transport between these Rydberg atoms. So each of these molecules I discuss here will be later replaced by a Rydberg atom. And only one of these Rydberg atoms is excited to another Rydberg state. So don't get confused, the Rydberg atom itself is here. For all the discussion, I have the ground state of the molecule. Yeah? We have an S Rydberg atom and a P Rydberg atom, let's say something like this later on. Okay, so why did people think about excitons, or came up with a concept like excitons? Well, this is an exciton is a single electron excitation in an extended system, in a large system, let's say crystal or whatever, or even an ensemble of molecules. And I mean, maybe you do not think a priori about that, but people simply measured photo absorption and emission from these extended systems and got really confused about the lines they saw. They did not have anything to do with what one would have expected from isolated atoms or small molecules. So the question really, what motivated them was, how does an extended system absorb photons and dispose or transport the energy which it has acquired through this photon or these photons. And again, this is quite topical in these light harvesting systems, which really show energy transport by exciton transfer. What could be the analogy? Of course, this could be atomic absorption in a dense gas, where you also could think about some transport from one atom to another. But there's, of course, major differences to a crystal, where the experiments were done in the beginning. And this is a crystal that has vibrational modes, phonons. It has translational invariance. It's a lattice, it's regular. That's very, very important for the structure of this excitation, this exciton excitation. And then, once you're so regular, you have the downside. Of course, you can have impurities and defects if you start from a very regular arrangement. And that plays also an important role, for instance, to localize excitons. Yeah, an exciton is normally coherent excitation delocalized over the entire crystal, let's say. But if you have a defect, that allows you to localize the excitation, again, in a very small spatial region. And because of this kind of phenomenon, you know already that a single electron excitation must be a linear combination of localized atomic excitations. So you don't know where it sits, right? That you know very well from your Rydberg gas experience, I guess. And this is the same here. That's what people, of course, realized and started to use. And the only thing you have to respect to start with, and you know you have to respect, is that this linear combination has to respect the translational invariance in your lattice. It's kind of a block condition. So the ideal state of vector k in reciprocal space or corresponding wave packet is given. And this is what led Frankel then to his exciton concept. There's an alternative viewpoint by Vanier and Mott, and that is that you simply think of, let's say, kind of insulator or something like that, really condensed matter system, where you have bands, you have valence bands and conduction bands, and you excite basically, let's say, an electron into the conduction band, and then there is a hole generated, of course, in the valence band, and this hole moves together with the electron in the conduction band across the whole crystal. That's another kind of formulation of this excitation. And they have two different characteristics. I will just come to that. So this is the history. Frankel came up with that in 1931. Non-conductive electron excitation beyond atoms. And it's called zero radius or Frankel excitons. And the reason is relatively simple. The reason is that he thought about, so this is our crystal or lattice of atoms. He has basically an excitation of the electron where the exciton radius is not larger than the next neighbor spacing here, AL. Yeah? While Vanier came up with this large radius excitons for inorganic semiconductors and ionic crystals, also by Mott a couple of years later, and there the radius of the exciton actually is much larger than the next neighbor spacing. Yeah? So that's the difference. And you can see that we will mainly be dealing with this Frankel type of excitons if you think about molecules which are fairly far separated from each other. So the excitation in each molecule is still kind of localized on the molecule. It's not comprising all the other molecules in the chain. So I will discuss the approach here mostly as it is described in this book, Photosynthetic Excitons, by von Amerongen, Vulkanas, and van Grondel. And you might want to have a look at that. It's not very recent, but I think it's a very good book. And now I will come directly to molecular aggregates, because that's what we want. And an aggregate is just by definition an ensemble of identical neutral molecules, or units. I call it unit later on, because remember we want to replace the molecules with Rydberg atoms eventually. And single excitation leads to exciton dynamics through dipole-dipole coupling. Yeah? And this is, again, what we like and why we are studying that. And as I said, it's much closer to Frankel's concept because it's localized. And how do we start? Like always in atomic molecular physics or chemistry, we start with the Coulomb interaction because there's nothing but the Coulomb interaction. So the Coulomb interaction now between two charge distributions is given like that. You can think of that in the one charge distribution is one molecule with many, many electrons, and the other one basically all the other electrons. And of course these electrons interact as Coulomb force where normally in the energy, interaction energy is then given like this. Now, we take, of course, the limit that these two molecules are very far apart and bring them together. That's the usual approach. So we make a multipole expansion, right? In terms of the distance between these two charge distributions or molecules. And here we can now expand this interaction energy of two molecules, I and J, separated, as I said, by a certain distance, Ri minus Rj. In terms of the multipole expansion, you probably know from other contexts. So the first term is, of course, the Coulomb monopole term itself, Q1 times Q2 over R, where Q is simply the total charge of the system, so the charge distribution integrated over space, P3R, this is vector, of course. And this, of course, occurs only if you have a charge system. Otherwise, if the molecules are neutral, this does not exist. The next term is the dipole, where the dipole of one molecule interacts with the charge of the other one. Yeah? Therefore, this is only 1 over R squared. And again, of course, this requires that one molecule is charged, Q1 or Q2. If we have two neutral molecules, forget about this one as well. And then comes the third term, and this is now the interaction of the dipoles. And this does not require, of course, a charge on each system. This is induced dipoles, that's what we want. This is the interaction, kind of largest interaction between two neutral charge distributions, parameterized by their dipoles. This is given here, and then can come to higher terms. This is the quadrupole tensor and so on, but we won't need it, so we will really be mostly dealing with this one. And of course also with the true dipole here, because the dipole is the photoabsorption dipole, and that's the same thing as I discussed yesterday. Okay, so when actually do these kind of terms play a role? This is important for charge transfer modes. If you want to transfer charge in a system, you know, if you have already charge and you transfer that through your molecular chain, then of course these interactions are important. And as I said, for us, for neutral systems, only this one. And now you can, of course, think immediately what is the condition that we can apply that. And of course, the condition is that